Welcome, everybody. This is SMPTE Standards webcast on SMPTE 2110. And why does it matter? Before we get too far along, I do want to do a little bit of housekeeping. I am Joel Welch, SMPTE's Director of Education, and welcome to friends, colleagues, guests, everybody. So expect a lot of questions during today's webcast. We're going to take a couple of breaks here and there. But if this is your first time with SMPTE Standards Update webcasts, they are quarterly, about 90 minutes long. We extended them from 60 because people wanted to ask more questions, and we regularly went over the 60 minutes previously, and we do cover select SMPTE standards and topics. We also make them free to everybody because SMPTE Standards work is such an important part of what we do. As with our other webcasts, sessions are recorded for on-demand viewing convenience. We do put them on the SMPTE.org site and publish them to YouTube, and everybody is welcome to watch them and share them. As I said, our speaker is John Myatt. He's CTO of Infrastructure at Imagine Communications, and he is a SMPTE Fellow and an Emmy Award winner. So with that, John, I'm going to turn the floor over to you.
Okay, thank you very much, and I hope everyone can hear me adequately. My name is John Myatt. I am, as mentioned, CTO of Infrastructure at Imagine Communication, but for the purposes of today's webinar, whoa, that was a lot of steps forward. I'm also the editor in the drafting group of the SMPTE 2110 standard, and it is extremely an active drafting group, meaning that there are about 140 participants in the drafting group, and in any typical call there are as many as 40 or 50 people in the call, so it has been quite an interesting activity to move the standard through the hoops from idea to very nearly reality. SMPTE has been involved in creating and publishing transport standards for IP for a long time. So the SMPTE 2022 family, for example, is pretty well known, pretty well established in the industry. There's really two different things going on in SMPTE 2022. The SMPTE 2022-1, 2, 3, and 4 are about taking MPEG-2 transport streams over IP. So these are commonly used in signal transmission for studios to transmitters, or for event contributions, or distribution from network to affiliates, or other cases like that where you have a fairly highly compressed signal. Usually the codecs have some latency involved, and so those standards were published really quite a while ago. They built off work in other groups, most notably the ProMPEG forum. So the techniques used in SMPTE 2022 1 and 2 have actually been around since around the year 2000 or 2001. A little bit more recently, the SDI over IP 2022 5 and 6 were published by SMPTE in 2013, but again built on work done in the ProMPEG forum before that, and the Video Services forum as well. In both cases, those are multiplex standards. So there's a bundle of video and audio, and in the case of transport streams, sometimes several programs worth of videos and audios. And they're all bundled together in one bundle and carried around as one single package through the IP network. Now that's great if you want all those parts, but if you're in, say, a production situation, or you're in a case where you have a recipient who really only wants one part, they still need to take the whole stream from the network. So for example, if you have, say, an audio desk and you're trying to capture a couple of audio channels from a program in 2022-6, you wind up receiving the entire video bundle, which in 2022-6 could be 1.5 gigabits worth of IP data, simply to pick out 1 or 2 audio channels. So that's a problem in in applications that need it. So this led us really into the realization, of course, that IP itself is a multiplex standard. If you look at Ethernet or other ways that IP is carried, every IP packet has a header, and every packet can be part of a different stream inside the IP payload. And so effectively, 2022-123456 are multiplexes being carried inside of a multiplex. So while that seems very flexible, in practice we aren't using it that well. And so SMPTE 2110 has a different approach. In SMPTE 2110, we put each part of the signal into a different stream in the network. So the video, potentially each of the audio channels separately, potentially several flows of even ancillary data streams, are all separate IP streams that are separately routable in the network. So this way, the operator of an audio console can punch up whatever audio channel they want. A captioning box might punch up the captions only and not the video, and so forth. Each recipient can get exactly what they want and really only get what they asked for. So this leads to a tremendous improvement in the efficiency of equipment that's trying to deal with particularly audio and other relatively low bandwidth signals. So in making the standard, we thought about, well, could we write one giant document that dealt with everything? And that's challenging for another number of reasons. It would be a pretty long document, and also it would be kind of a long process to get through. The SMPTE standards making process is at its best when the documents are, relatively constrained in terms of scope and what they're trying to do, so you can really get focused on making a perfect, albeit fairly small document, and then proceed to the next perfect but maybe fairly small document. So we split this standard into a number of parts, both to help us get through the process and also to make it a little more digestible in terms of really, reading and understanding them. So the first part that we're going to talk about is the -10 document, which is the kind of system model of how timing and timestamps and so forth work. So the Part 10 document is really focused on how do these separate streams, once we split up the video and all the audios and maybe an ancillary data into separate streams and IP, how do we keep all those parts synchronized to each other? So SDI was good for this, because SDI, when you bundle it all together, they're tightly bound from a timing perspective too. You get those bits all in a certain order and the timing is absolutely right there. In 2110, each of them are separate, they arrive separately, they might arrive reasonably dispersed in time. But each of the parts, the audio channels, the video frames, so forth, have timestamps. So the first thing we do is we use SMPTE 2059, our new PTP timing standard, to distribute time, both frequency and phase, to every device in the system. So every camera, every microphone, every audio sampler, every audio console, every captioning box, you name it, has a sense of exactly what time it is. It's the equivalent of sync and time code and word clock all mixed together in one. So PTP is a fantastic standard. I'm sure there's a separate, different webinar about that, and that's mostly what I'm going to say about PTP in this one. But each device has now a perfect sense of time, frequency, and phase. So if you're sending a signal, whether it's audio or video or ancillary data, you mark it with an RTP timestamp that is the sampling time. So if you're making a camera, it's when you sampled the light from the image. If it's a microphone, it's when you sampled the audio from the air. If it's a playout server, it's sort of the equivalent thing, but obviously you're not actually sampling, you're just playing back. And so you mark these timestamps, and then the receivers can compare the timestamps between, say, video channels and audio channels in order to properly line them up with each other. So this is really a tremendous improvement over what we do today. Because what we do today is we assume that when signals come out of, say, a camera or something, they're lined up with each other, and we use Genlock to make that be true. But by the time they've gone through the plant, we don't really know how much they've been delayed by. Now that they have timestamps in them, you know exactly what they've been delayed by, and you can match those timestamps up to pull everything together. So a lot of the audio to video adjustments that we have to do today by hand can be automated and can happen as a matter of course in the network going forward. This really lets you do a second thing which is important, which is in this system you can mix and match videos and audios from any of the sources in your network, because PTP is used to synchronize them all. So 2110, what's it about? Well, it specifies exactly how we'll use SMPTE 2059. It specifies first that we will use it, and it specifies a little bit of how. It specifies how the RTP timestamps are calculated for video and for audio and for ancillary signals. It specifies kind of the general requirements of the IP streams, requirements that really go across all the parts of the standard. And it specifies a thing called session description protocol and says that we'll use it. And I'll talk in a second about what SDP is. And of course, the actual formats of the video and audio signals are the subjects of the other parts of the standard. So a little bit about this session description protocol, SDP. It's from the internet, it's an RFC, and it's a little text file, really is small, that has the set of metadata that tells the receiver what it's expecting inside the stream. And so this is the information a receiver knows, or receiver needs to know in order to actually receive then the stream of packets for a given video signal or audio channel. So the senders, things that put streams on the network, they expose an SDP for every stream they're making. And then the control system conveys that SDP information to the receiver. Now, the key thing in any SMPTE standard is to understand the scope, and that control system is actually out of scope to the 2110 standard itself. There's a separate group in AMWA working on a thing called NMOS that is all about that. Maybe that's the subject of a webinar of its own, but it's not a subject of this webinar. But just as an example, here's an example of an SDP file. It's pretty small on my screen. It's probably pretty small on your screen. And RFC 4566 describes what all these fields mean. And SMPTE 2110 more exactly describes the new ones that are added in 2110. But this is an SDP for a video signal. You can see it's got things like width equals 1280, height equals 720, frame rate is 60 over 1001. All the things you'd need to know to say, hey, this is a 720p signal. So that's kind of the system timing. And I'm going to talk about video, and then we'll break for questions right after video before we go on into audio, which is where all the fun begins. So video in 2110-20, that being 2110-20 is the standard for how video is sent. The first big thing to note is that we only send active video. We don't send blanking anymore. People mostly have gotten rid of their CRTs. The blanking is really an artifact of horizontal retrace and vertical retrace. And if you're under 30, you need to go find someone older than you to ask what those even were. I look forward to a day when there's no more retrace. So 2110, first and foremost, we don't send blanking anymore. Second, the standard supports arbitrary image sizes. So you're not locked into 1920 by 1080 or 1280 by 720. The 2110-20 standard lets you send 1372 by 953 if that has a business value why you want to send that. It's interesting, you can send a bug without sending the whole picture around the bug, for example. And it supports image sizes up to 32K by 32K. So, UHD is neat. 8K is going to be awesome. By the time we're doing 32K, well, maybe that'll be the next guy's problem. SMPTE 211020 also supports a wide range of sampling formats and color systems. And so, we think in terms of, in the television broadcasting world, it's, 422 10-bit YCBCR. But in the post community, in the digital cinema community, and some of the other filmmaking operations, there's all kinds of color spaces that are used, including in XYZ and RGB and ICTCP and so forth. So 2110 actually supports all these different color spaces, many of which, some of which were not supported on SDI very well. And it supports them in 12-bit and 16-bit and 444 and so forth. There's also special forms for key-only channels, so you can send an alpha channel without sending, that's really just a single alpha component. And of course, you can send fills. And 2110 has support built in for HDR, for PQ, and for HLG. Now, the samples are very tightly packed in. So this is an example of how the 10-bit 422 samples are packed in. So you've got 10 bits of one, 10 bits of the next, 10 bits of the next. And you can see like 2 bits plus then 8 more in the next row, and so forth. So if you're in 10-bit, it's packed in. If you're in 12-bit, it's packed in a little differently. But it's always very tight. We're very efficient with how we put things on the wire. Now, how much bandwidth did we save by getting rid of the blanking? You don't think the blanking's very big, but the blanking's really big. So in the 5994 system, it's, about 16% that we saved by not sending blanking. And that's significant, right? In 720p, it's worse. In 720p, about 25% of the bits, so you say HD is 1.5 gigabits, 25% of those bits are blanking. They're just filler. Why do we send them? Well, we don't send them anymore. In the 50 hertz countries, it's far worse. So in the interlace system in the 50 hertz countries, 30%, 30%, is waste, is blanking. And in 720p in 50 hertz countries, it's actually almost 40% of the bits were wasted in blanking. So there is a benefit to not sending blanking, beyond just blanking being old-fashioned. Not sending blanking is actually saving a tremendous amount of network bandwidth that you can, of course, then use to send other signals. So I'm going to stop for any questions on the video side, if there are any.
And there is one question in the queue from Nicholas, and he was asking about where does SMPTE 2110 stand regarding 4K compression? When will this specific part be covered? He also says thank you for the webinar.
So 2110 actually does 4K and 8K and 16K as uncompressed. So literally, UHD is sent as 3820 by 2160 in whatever color resolution is used as uncompressed. There is discussion about whether to add a compressed form in the standard, but there's not any current draft activity to create that. That's a future activity potentially.
And
other questions from
Ali, does the savings you listed exclude the use of VANC for instance to data or HANC to carry audio?
So audio is transported separately, and so the savings I listed, I didn't correctly account for audio in it, but the audio is in the rounding error. So each mono audio channel consumes about 10 megabits, which is, like I said, in the round-off error of the numbers of gigabits for these signals. Similarly, the VANC data is sent separately. I have a few slides about that toward the end. So yes, there's, in the round-off error between those numbers, the video, the audio and the ancillary data are kind of in that error. But that's why we don't send the blanking. We do send the audio and the ancillary data, but separately, so they can be routed separately.
Ali says thank you, and that is the last question.
Great, so we'll proceed with audio, because as everyone knows who's been involved in television production, the video gets working right away, and we spend the rest of the time figuring out audio. So for audio, we have actually two documents. There's 2110-30, which covers the sort of PCM audio, this kind of standard audio case. And then there's -31, which covers a transparent transport of AES-3, and we'll talk about why sometimes you need that. Now, on -30, there's some important facts to know. The first one is that 2110-30 fundamentally says use AES-67 audio. So the Audio Engineering Society, AES, spent a long time developing and standardizing AES-67, which is the harmonized audio over IP standard. The audio industry actually had a very large number of proprietary systems. At one point there were as many as 10 or 12 different audio over Ethernet systems out in the wild in use. They then sort of did a long period of standards work to come up with AES-67. It's a great system. And so the first thing we decided in SMPTE 2110 is we said, well, let's do audio the way the audio industry does it, because then we can use audio consoles and microphones and things that the audio industry already has, instead of inventing a different way to do audio for television. So the most important thing about 2110-30 is that it's built on AES-67. That said, the audio industry also prides itself on its inventiveness. So AES-67 talks about a lot of things that you could do. It says, you know, you could do 96 kilohertz, that you could do 44.1, that you could even do 32 kilohertz audio. It says that you could have packet times of 1 millisecond or 500 microseconds or 250 microseconds, or so forth. So there's a lot of things that AES-67 says you could do, but there's really only a few that AES-67 says you shall do, or that you must do. Every receiver must support or shall support these things. So this is sort of the list of what AES-67 says that every receiver shall do. So every receiver is required to do a 48 kilohertz sampling, which is good because that's what we use in television too. Every receiver is required to support 1 millisecond packet time, meaning there's 48 samples of audio for each channel in that packet because it's 1 millisecond worth of audio, and so forth. You're required to support as a receiver between 1 and 8 channels per stream, and that's configurable, but you have to deal with whichever way you get it, and you're required as a receiver to deal with 16-bit or 24-bit audio. So those are the things that are required, and as SMPTE in 2110-30 we said, great, those are good things. Now, if you wanted in your facility to operate in some operating point that isn't in that list of things that everybody has to do, then you have to read the specs really, really carefully to make sure that everything you buy supports the mode you're trying to operate in. But the good news is that this zone of the required features is pretty reasonable. It's the vast bulk of television production and distribution use cases, 48 kilohertz, 1 millisecond packet time, some small number of channels per stream is a great way to do it. Now, as a video person, because as some of you who know me know, I came from the video side of the world. IP digital audio, when you are a video person, kind of looks like this. It's, there's some microphones, and then a miracle happens, and then there's a mixing console. And even for people who understand that, no, it must be digital audio, okay, you know that there's some A to D converters between those microphones and whatever that miracle is, and hopefully those converters are even sampling things at the same time. And there's a sampling rate, and it usually is 48 kilohertz. Now, people who understand networks say, okay, well, I know the audio is put into packets, and so here I show you I'm putting 4 microphones into each stream. And obviously there must be a switch, because otherwise we wouldn't be a network, we'd just be wires. And then to make it really complicated, of course, there is some kind of PTP timing generator, and that PTP timing goes through the network, and it generates the, ultimately the word clock that's going on inside that A-to-D converter, so it's setting the sampling rate and frequency and phase on that converter. And it's also generating sort of the strobe that each of those packets in red was sampled at the same time, or each of those samples in red is sampled at the same time, and then it's picking, okay, so that red packet, when it's a red sample, when it's put in the packet, what is its timestamp? And so usually, again, we operate at 48 kilohertz, we operate at 1 millisecond packet times, and how to pack those into the packets is a choice in a facility, because you might want, that's how things are routed inside the IP. So if you want to route in stereo pairs, that's great, many people do. If you want to route larger slugs, maybe 4 channels or 8 channels together, there's some facilities where that's very logical. There may be facilities like sound stages where you really want to put every mono channel in a separate stream. And you can do that too. The standard allows it. This notion of channels per stream is the one kind of key factor when you're organizing the audio. You have to think about, do I send every channel separately, which generates lots of streams and it generates lots more configuration, and it's actually, because it's kind of, a lot of work, it's not that typical so far in projects we've done. Sending slightly bigger streams, maybe stereo streams. Stereo streams is pretty standard. Bigger streams are common in audio-only environments, but I haven't seen them that much in television yet. So 4s are sometimes used. Haven't seen too many 8s. So when you're switching an IP, it's, you switches all of those channels. Now, most devices have some sub-selecting downstream, so you can send it as a 4 or 8 channel stream, and then down at the end device, you pick, okay, well, I really wanted channels 1 and 2 of that. Different devices, when you are purchasing audio equipment, make different trade-offs. So when you buy a digital audio piece of equipment, you might think you just ask, well, how many channels does this do? But you really also have to ask, how many streams does it do? Can it do, 64 streams, each with 1 mono channel in them? Or can it really only do, say, 8 streams with 8 channels in each, and that's the only way it can operate? So you have to, as you spec out equipment or think about design, both questions matter. So you have to think through both questions. Now, audio, as I said before, is pretty tiny compared to the video. An audio signal, a 2-channel stream is around 2.5 megabits. An 8-channel stream is just around 10 megabits. Those seem like a lot. It's uncompressed audio until you put it next to the video, and then it just disappears into the shadow. Now, what about non-PCM audio? Because this 2110-30 really is AES 67 audio. We've added a few channel descriptors and other things, but it's fundamentally AES 67. So non-PCM audio is things like Dolby E or Dolby AC3, or sometimes there's even AAC in some markets. There's also some non-audio signals that people send around, which again, we route them in AES3 today, so we think, oh, well, we should have a way to do it. 2110-31 is a bit transparent tunneling of AES3. So every single bit in the AES3 signal gets put over IP and is available at the other end. So it can handle non-PCM audio. It can also carry PCM audio that use the user bits, because the AES3 signal has user bits in it. And over the years, some people have used those for things. It also handles the C bits and the V bits, and there's channel status bits and so forth that are used in some configurations by some people occasionally. So all those things tunnel through in -31. Of course, when you're tunneling AES3, it's always stereo, because AES3 is always stereo. But of course, what's inside it, like in the case of Dolby E, might be more channels, might be more than 2 channels. So that's sort of the story of audio. Does anyone have any audio questions? There's always at least one audio question.
And there is a question from Victor. He says, can Dante audio be integrated with 2110?
That is a common question. Dante is one of the, there used to be 10 different proprietary audio systems. Now there's really, Dante is the biggest remaining one of the proprietary era systems. It is very widely deployed in the world. Some Dante equipment has an AES67 compatibility mode. It depends on, sort of when it was built, what software version's on it, which vendor made it, so forth. So it is a good question to ask of your actual equipment provider of your Dante equipment as to if or when it will have an AES67 compatibility mode. And the Dante AES67 compatibility mode, assuming that it's compatible, should be compatible to 2110 as well.
Okay, let's see. Couple of comments here. Henning says 2110-31 is, of course, non-SRC. And Jovo says on, I think it's read deliver side, alignment is access unit based, hence the question. And Jovo asked the question in terms of time synchronization. What does correspond to time of video, audio, data access unit? The timestamp of the first RTP packet delivering that access unit or something else?
So, good questions. So for video, clearly the access unit is a frame because that's kind of how video works. For audio, the access unit in PCM audio for -30 will be the, is as small as a packet. So you can chop the audio all the way down to 1 millisecond packet boundaries. Each packet is completely self-sufficient, but they don't obviously have very many samples. So 1 millisecond packet time will have 48 samples in it. And the RTP timestamp of that packet is the sampling time of the first sample in the packet. For -31, for the AES, the transparent AES3 mapping, again, the timestamp is taken to be the sampling time of the signal contained in it, so the AES3 signal. And the access unit will depend a little bit on what is inside the AES3. So if it's Dolby E, for example, typically you have to sort of take that in either 33 millisecond or 40 millisecond chunks. If it's something like Dolby AC3, it depends a little bit on the AC3 mode, but it's a fairly long chunk. I don't remember, I think it's 24 milliseconds, something like that. So there are different access unit times according to what payload is inside the AES3. Hopefully that addressed the question.
And there are a few other questions, but they're ancillary data related or compatibility or metadata related. So
let's talk about ancillary data. Yep. So of course, video and audio we've been dealing with for years. In SDI, we introduced the concept of ancillary data, usually buried in the VANC or the HANC. And so SMPTE 2110-40 is the part of the standard that describes what to do with ancillary data. Sorry, the slide didn't move. There we go. So 2010-40 is the ancillary data part of the standard. So over the years, we've developed many, many things that we put in the SDI ancillary data space. There's obviously people think of captions or teletext or subtitles, but equally we've got all kinds of other stuff that's been put in there. So people put triggers and cue tones and downstream equipment triggers. Advertising triggers have now become very common, like SCUDY 104. So some of these signals are very tightly related to the video essence. Things like the SCUDY 104 triggers, or AFD is a good example, are very tightly related to the video signal itself. Some of the things in ancillary data are just separate essence that's along for the ride, like captions, where it's timed to the scene, it's timed to the content, but is it really on? Is that character really on this frame or that frame? Is maybe not 100% important. And then there's stuff that's really just using the pipe and riding along. Sometimes we have downstream equipment triggers that are, information. Or I saw a network once that sent messages that would appear on the screen of the IRD at the affiliate. Those happen to be buried in the ancillary data. So audio is actually formed as ancillary data packets. And so embedded audio at one level looks just like other ancillary data. But because we have a whole audio system that's the way the audio guys do it, we don't use this method for audio. So that's like the important first rule. And so for ancillary data, our friends in the IETF, actually, the Internet Engineering Task Force, have a draft RFC that'll be done very soon. It's essentially done now, but like many things, getting from done to finished is sometimes hard. There's a draft RFC that says how to take ancillary data packets and wrap them up into IP datagrams and put them in RTP. And it's done, pretty generically, regardless of whether they're, captions or teletext or whatever. There's any well-formed ancillary data packet can be mapped into IP. If you want to see the work in progress of that standard, those are actually publicly available. So if you Google around a bit, you'll find the current IETF draft for ancillary data in IP. And so the SMPTE standard says to use that RFC and how to set some of its timestamps and other requirements to map into SMPTE 2110. So that's a great example of, not everything has to be done in the SMPTE. We can work together with the IETF and with the AES to get things done more quickly. Now, an interesting thing happens if you start taking the ancillary data and putting it in separate streams in the network. You can now do breakaway routing of ancillary data. And that's never a capability we've had before in television. It's always been so tightly coupled to the video, it just switched with the video. But now you'll be able to do breakaway routing of ancillary data. So this is an odd capability, and it leads you to ask, what could you do with it? So today, if you think about putting together, say, a net string at a network or something like that, we loop the signal through a lot of VANCE inserters to insert the captions, to insert the downstream triggers, to insert some other downstream in the future, if you need to make SDI, which is an interesting if, but if you need to make SDI for some reason, instead of looping through inserters, you would compose it. So you would route all of the different ancillary signals you want in there to the final widget that then takes all those plus the audio signals plus the video and puts them together into SDI. So it's a little bit different operation. It actually simplifies the block diagram of the net string quite a bit. If it's really, instead of looping through inserters, it becomes assemble the signal you want. So you'd get an environment like this where, imagine, at the left you've got an SDI signal, and then a 2110 gateway would break that into video, some audio streams, some ancillary streams, because you're allowed to make more than one. You could actually, in that SDI, you might have captions that you put onto one stream. You might have video-specific stuff like AFD and so forth that you put on another stream. you might have some unrelated triggers that are on a different stream yet. Then you could have devices that generate data directly into 211040. So you could have your captioner that's, got your whole captioning system behind it, and that captioner could be generating 2110-40 directly. You could have a downstream triggering system that generates 2110-40 triggers. Those signals all show up in the network, and then at the right-hand side, when you're making a new SDI, those captions and downstream triggers and some selection of audio channels all get mapped straight into the SDI. So again, you get the effect of generating the SDI that you want, but you're doing it instead of looping through inserters, you're now assembling it at the end of the chain. So that's sort of the summary of the VANT system. So today we've talked about 2110 and that it enables you to separately route over IP the video, the audio, and the ANT signals. It uses PTP timing, and in fact it requires PTP timing. One of the interesting effects in SMPTE 2110 is that within the network, all of the signals are synchronized. So, in SDI, it's a really good idea to line up all your signals, and you'll only get decent switching if they are lined up. In 2110, it's actually required that all the signals are synchronous to the PTP clock. 2110 saves bandwidth by not sending the blanking, of course, and the fact that all those signals are lined up and that we've used PTP to distribute time lets you do breakaway routing of all the audio and lets you do breakaway routing of the VANTs. So let's hit the questions that are in the queue.
And we do have a number of questions, actually. So before I get to them, and they're starting to come in even more, I'd like to remind folks that verbal questions are preferred. You will go to the top of the list if you agree to ask a verbal question. If you do not have a microphone or do not wish to ask a verbal question, type them into the chat box and I will read them to our speaker. And some of these questions you probably covered, but I'll ask them just for good measure, if you don't mind, John. From our good friend Madeline, is HDR metadata accommodated in 2110-20, for example, 2086?
Yes. So in the example SDP I put up many slides ago, the 21-20 SDP includes metadata about HDR. It includes, obviously, with reference to 2086, so you can refer to the PQ system or the HLG system. And but if there's dynamic metadata, there is a SMPTE working group creating the ancillary data packet for carrying the dynamic metadata, and so you would use the -40 to actually transport the dynamic metadata.
Thank you. And in all fairness, she did submit the question quite a while ago. Let's see. From Ronald, is 2110 cross-compatible with other VoIP standards like NMI?
The short answer is no. The 2110 standard is a fully uncompressed standard. So NMI is again a proprietary standard from NewTek. It is licensable, and several people have built it into products, but the SMPTE 2110 standard describes a specific uncompressed video over IP methodology.
Very good. And please forgive me for mispronouncing the first name, I think it's Yovo. Can you provide a bit more information about the SDP discovery process?
So the SDP discovery process is actually, the SMPTE standard simply says that devices make the SDP available. But the envisioned ecosystem is that the NMOS works. So there's a standard in the Advanced Media Workflow Association called NMOS, stands for Network Media Operating System or Operating Standard, something like that. The NMOS work is, has a discovery process where you can discover all the nodes or all the devices in the system. The devices register into a network-based registry, and then Of course, in the process of registering, they also expose, or the network collects their SDP information, and then that SDP information is used as part of connection management, which is also described in NMOS. So if you go to the AMWA website, AMWA, there's a link there to the NMOS specific group page, and the NMOS specifications are all publicly available on GitHub.
Okay. And again, forgive me if I mispronounce this name. I think it's Ghislaine. If you wanted to carry ancillary data, would you still be able to do it as part of blanking? Or does it have to be a separate stream since blanking is removed? In other words, is blanking systematically removed in 2110 or is it optional?
It's gone. Blanking is not transported. If you want to send ancillary data, send it using -40.
Thank you. Robert asks, what is the expected accuracy of the PTP timing?
The expected accuracy of SMPTE 2059 PTP time is around a microsecond or a half a microsecond. I'm not an expert on PTP, so I will defer to one if one is on the call, but I didn't look through. There's a lot of attendees on the call.
Yes.
So I believe that it achieves, in the order of microsecond or half microsecond accuracy. And remember that we're in the early days of PTP, so as people's implementations mature, I suspect it will tighten up even more.
Great. Let's see. First, Chris says, thank you for the webcast. Can you give an update for the timeline for publishing the final SD 2110 standards?
No, I am forbidden by the Engineering Standards Vice President from making any prediction as to when this standard will be finished. And that's really true, too. I'll get yelled at deeply if I say it's going to be done next week. But that said, it is progressing very well. The main parts, the 10, 20, and 30, have gone through the process, have gone through FCD ballot, have passed FCD ballot, and are in comment resolution. And 90, the vast bulk of comments are actually resolved. So we're down to really the last handful of comments, and even those, I believe, we see a reasonable path to resolution at this point. So it is, as we say, all but finished, which is to say, not finished. But that said, there are 140 members of the drafting group, and every vendor involved every vendor who wishes to maintain relevance in the industry is involved in the drafting group. Most large customers are also involved in the drafting group. So it is a very good representation of the industry, and there are no, I'll say, substantial technical changes really left on the table. It's all down to, wording and references and, the kinds of things that usually take the last few weeks of work. So we are really down to the, down to the last bits on here, but I don't believe that the state of affairs is holding up much in terms of progress. I think everybody who wants to be involved in making or using equipment in the early days is probably become a member of the group by now.
Excellent. Okay, Ali asks, is there a way to deal with analog VBI that is currently used in SD, SDI?
Not really, and that's an interesting challenge in 2110 is that we did not define an encapsulation for the VBI signals of the analog VBI signals of SD. If they are VANT signals, if they're formatted as ST291 VANT signals, then they would get transported with -40. But the a traditional signal like vertical interval tests or something like that, or would be a challenge. Now that said, the traditional teletext and subtitles, the common practice in DVB countries is to map those into OP47, and OP47 is a VANTS packetized representation of subtitles, of teletext and also manages subtitles as teletext. So most of the signals like that have a substantive use now have a VANCE data type of format. But actual analog like AMOL or something, there's no representation of in 2110.
Okay, next question. Have you discussed how to address the flows in 2110 regarding multicast addressing, video, audio, ANC?
Yep. Every device is required to support IGMP and to support IPv4 multicasting, and we expect the common use case to be that senders will send on multicast groups and that receivers will tune into or join multicast groups as part of the stream selection process. That's what's envisioned in the NMOS work as well, that what's communicated to the receiver is the multicast group to join. And then we expect the network to do a correct job of pruning and snooping multicast to make that happen correctly. In terms of the specific, is there a exact pattern? No, it's up to facility design to decide what is the correct, or what organized system of multicast addresses will be used. And we chose that in part because we had feedback from different customers that they had existing work or other constraints that they didn't want a pronouncement of, this addresses shall be exactly structured like this. Sometimes there's other things to work around in a facility, so people wanted flexibility to choose the addressing schema themselves.
Great. And we do have an audio question from our guest, Howard. Howard, you are free to speak to John.
Hi, John. Yeah, thanks for doing the presentation. So I have a question about PTP. So PTP is used to coordinate video and audio so that from the sender side that those two pieces are lined up. But then on the receiver side, if it receives the stream sometime later, it doesn't need, does the receiver side need to be synchronized for PTP as well?
Yes, receivers need to use PTP also, because the PTP is the frequency reference for reconstructing the signal. So all the generation of display clocks and word clocks for audio and so forth in the receiver are derived from PTP. And also the receiver needs the PTP time base in order to successfully usually adjust its buffers or things to kind of home in on the signal. It's really the only way the receiver knows what time it is. So you could make probably a receiver that didn't look at PTP and just looked at the signals and used the relative time between the video and audio to sort of guess its way. But that receiver would also be trying to invent its word clock and video display clocks and pixel clocks without a proper time base. So I think the notion really is that the receiver, the PTP is there in the network, and a well-designed receiver should expect to use it.
Okay, so maybe to ask this another way is that if we recorded a 2110 RTP stream on Wireshark, say, and then we played it back, then you'd have to have some way of playing it back such that the timestamps are adjusted. Then is that a valid statement? Yes,
if you introduced, days of delay because you recorded it and then played it back the next day, you would have to get it to work right, you would have to adjust the RTP timestamps in every packet to match the amount of, to match the current time, or the difference between the time when you captured it and the current time. Otherwise, those RTP timestamps would be, way off in the weeds compared to the current time.
Right. Okay. Thanks for your answers.
No problem.
Okay, next question. I don't think I've asked this question. What about tally in SMPTE 2110?
Tally in SMPTE 2110 is handled the same way tally is handled in SDI, which is to say, not at all. It would be neat. It's an interesting piece of work. I'm staggered, actually, that in 2017 we still use GPIs, but we do. And so there's nothing specific in 2110 for triggers like tally or GPIs. I wish there were. I think that's the undone piece of work in this IP transition, is really replacing all those GPI relay closures. But that said, I'm fully occupied doing 2110 these days, so if someone else would like to start such a document, it's the world awaits it.
Thank you. Next question from Ben. Hi, Ben. Does 2110-20 support arbitrary frame rates, and what are the limits? Also, does it support transport of Bayer pattern / raw image data?
So 2110 supports arbitrary frame rates. Yes, you can describe, well, let me say it supports arbitrary but regular frame rates. So there's a field in the SDP that is exact frame rate, and it's specified as a ratio to integers. I don't believe that we specified a limit in terms of upper bound or lower bound, so you could have an incredibly low frame rate. I do not believe that we specified a way to say frame rate of unknown or irregular, so I don't think we put in support for irregular frame rates. If that turns out to be an interesting use case, a non-voter comment would be welcome, and we certainly, like all documents, will have a one-year review, so we will definitely be looking for feedback on use cases that we didn't include at the one-year review. In terms of Bayer pattern, I'm not an expert on imaging, so I'm a little bit guessing what you mean by Bayer pattern, but we support 16-bit 444 of a bunch of color spaces, but the Bayer pattern is an unusual one. So if it's a 4444, like a 4-component Bayer pattern, then I don't think we put in something specific for that. But it's not, it wouldn't be hard to add at the one-year review if it's missing, or to add in a parallel document that says, you know, generally follow everything about 2110, but do Bayer by using this method. It could be reasonably extended to do, you know, almost any regular pixel arrangement or regular sample arrangement.
Thank you. We have quite a few questions still. You doing okay? Let's see. Next one from Yovo. I hope that's how you pronounce the name. What reference designs on the receiver side can one take advantage of?
So in terms of free publicly available, I don't know for sure. I've heard a rumor that there's somebody put a design of something online, like an open source, but I've not tried it, and they think they referred to VSF TR03 in their press release about it, so I don't know if they just did that because 2110 is not published, which is true, or if they actually have updated to match what the draft says or not. But there is somebody that was doing that. It is slightly hard. There are a couple of IP licensing companies, people that design things for a living in order to, you know, then sell you the design to use in your product, that are involved in the drafting process and have been to the interops. So they'll certainly, if you go to your favorite FPGA vendor, they can refer you to at least one implementation each of, you know, so-and-so has an implementation that they license out. So there are IP blocks available from the usual vendors for implementations. And there was at least one group doing or purporting to do an open source software generator receiver. But again, I've not actually tried it, and I don't know for sure if they really implemented 2110 or if they implemented TR03, which is what their press release said. And I think you'll see more and more of that. On the audio side, there probably are some AES67 code bases out in the Linux world these days.
Okay, and we do have another audio question from our guest, Edwin. Edwin, the floor is yours.
Hi, thanks for the information so far, John. Can you say anything about what 2110 supports in terms of error correction and detection, lost network packets, and so on?
So the standard is built on RTP. So packets are sequence numbered, and so from the sequence numbers you can detect lost packets. The error correction model is actually based on dual transmissions. So we've taken the SMPTE 2022-7 approach, which is to send 2 copies on separate networks. We'll send a copy on each of 2 separate networks, and then at the receive side you can do a packet by packet merge from those 2 signals. There's nothing about SMPTE 2022-7 that is specific to the 2022 payload family. It actually can work with any RTP format, and so we've advocated and specified its use with the 2110 payloads. And in parallel, you'll see an activity going on right now of reviewing and tweaking the 2022-7 document, and the fundamental change we're making is to remove the references in it talking about using it with 2022-6 and changing it to talk more generically about using with RTP payloads. So the canonical design approach for error correction is to use 2 paths, 2 wires, 2 switches, 2 networks, and that way it covers all manner of ills. It covers packet loss during transport, it covers failure of switches, failure of optics, loss of packets due to dirty optics, all the different failure modes. Plus you can do in-plant maintenance. You can do as much as turning off an entire Ethernet switch because you've got 2. I don't recommend doing that in the middle of the Super Bowl, but it covers all manner of ills. It's really a very powerful system. It's actually more robust mathematically than what we've done for years in SDI, which is to have redundant power, redundant fans, redundant cross points. But if a line card fails, well, you're going to go look for a spare.
The next question you can choose to answer or not. I'm not sure you're going to be able to, but Carlos asks, how does 2110 reduce production costs?
Well, it should reduce the CapEx cost compared to an embedded audio plant because the audio is all separate to begin with, so you're not investing in racks and racks of audio embedders and disembedders. It also, in the fullness of time, should be able to reduce somewhat the setup time for events because the time stamping architecture should allow the audio delay trimming that takes a fair bit of time in setup during productions to be a little shorter. So we've put in things like that, or particularly the delay management features of the audio ought to enable setting things up a little quicker. But the detailed costing of equipment and pricing and so forth, it's hard to say exactly how that'll all stack out. I think it depends a lot on the scale of the project as well. An important thing to note is that in, say, traditional SDI routing, when you got above about 1,000 by 1,000 port SDI router, it got extremely hard to make bigger routers than that. I mean, we all can, but they're expensive. If you look at the equivalent bandwidth in Ethernet switches, the bandwidth equivalent of 1,000 by 1,000 SDI router, when you look at data center grade Ethernet switches, is actually the smallest switch. It's a very small switch. So the larger Ethernet switches in the data center universe now are more in the class of 10,000 by 10,000 SDI equivalent streams. And so it's a very different operating scale. So the largest productions that have very, very large scaling, IP is a tremendous cost savings. They wouldn't even really be feasible to do an SDI.
Perfect. Good friend Fred asks, please clarify studio video over IP, SVIP, OSI. Is it layer 2, layer 3? And also, how does Ethernet fit into SVIP?
So this application is effectively I'll call it layer 4 application. So we are defining, mostly by reference, RTP formats. We say that you carry them over IP, but you carry them the normal way. So IP is used. IP is the layer 3. The layer 2 is typically Ethernet, but nothing in this standard requires the layer 2 to be Ethernet. Layer 2 could be any If you had some other way of carrying IP packets that was cost-effective for you for whatever reason, you could certainly use it. Nothing in this standard requires that the IP be carried on Ethernet, but it does require that it's IP, and it doesn't require anything special about the IP except that it be IP in order to carry the RTP, and that we use IP multicasting as is a required part of it.
Thank you. Next question comes from Yoshiaki-san. Are timecode, UMID, etc. to be supported as the ANC data stream using conventional DID and SDID as their identifiers?
They certainly can be. Anything that it's carried in VANCE today can be transported with the -40 standard. The -40 standard is quite generic in its approach. The IETF document that we're working from actually is modeled off of SMPTE 2038, which is the way that we usually package VANCE data for transport over satellite and over IP links already, where we very generically take the whole ancillary data packet, including the DID and the SDID. So if you put something in ancillary data today, you should be able to put it in the -40 next week.
Okay. Next question is from Lars. P2P version 2 has some possible faults and extended monitoring is needed. Would PTP version 3 be considered as an update of Part 10?
If there's a PTP v3 at some point, we can certainly think about that, but we actually refer to SMPTE 2059, which is built on PTP v2. And yes, in PTP v2, you have to be, fairly diligent in your implementation. There are ways to cause or suffer from problems. In fact, I was at the EBU Network Technology Summit this week in Geneva, and somebody, I think it was Juniper, gave a talk about this very subject of, end-to-end monitoring for PTP in order to, really do proper monitoring. So there is there are white papers and talk out there in the industry about how to best monitor PTP systems to make sure they're really working as you expect.
Thank you. Ronald asked, does PTP support drop frame, non-drop frame, or does that also go away like blanking?
So SMPTE 2059, and part of why SMPTE 2059 is a fairly long document, is that the time that PTP communicates to all the devices is true time. So it's seconds and nanoseconds since the epoch, and the epoch was, April 1st, 1970. And then the SMPTE 2059 document then has pages and pages of incredibly detailed equations that describe how you create hours, minutes, seconds, frames in drop frame and in non-drop frame and in PAL and in NTSC, of course, and how you create also audio sampling rates and audio sample times and video frame times from the true time that's distributed. So it's really quite a piece of work, but it is built around the habits that we have today, particularly daily jam, and when you generate time code from PTP, whether you're generating drop frame or non-drop frame. So PTP itself just communicates true time, but SMPTE 2059 describes how to create all the different signals we use today from that true time.
Okay. Iftikhar asks, is there a recording of this webcast? And I'll take this one, John. Yes, okay, we are recording the webcast. We'll do a little light editing on it and post it as quickly as we can. It'll probably be available within a day or two. Thank you for the question. Lauren asks, what kind of interoperability testing has been done to date? Has this included testing over wide area networks on a global scale yet?
So SMPTE 2110 is primarily conceived of as a, sort of a campus area kind of standard that you would use within a facility or within a tightly coupled group of facilities. Nothing really prevents you from using it over larger distances. PTP has been shown to work over very large distances and many hops, but the use case, given the bandwidth of the signals, because say the HD signals are gigabits each, the typical use case, and certainly the interop testing we've done, has been focused on sort of the small and medium scale sizes of facilities. Now that said, in the execution of some of the recent world events where we've used 2110 in trial modes, we've used it over fairly long networks, but they've been kind of well-conditioned, privatized networks. This is really the name of the standard actually says something about studio video over managed IP networks, and that's really a key point in planning for the types of bandwidth that are used in these signals, is that it does need to be a managed network, a network that's been engineered for the purposes it's used. It's not a standard that we're advocating or designing to be used over the, quote, public internet. Now, I'm glad you asked about interop, though, because we have had a number of very large-scale interop events. The most recent one was, of course, at NAB. So at NAB, we had a interop event that was public on the show floor, and it was staged about 3 weeks prior at Fox Sports in Houston, who graciously provides a very large facility for doing that. There were, I want to say, more than 30. I think there was like 35, 36 vendors at least involved in the interop, and that's really meaning different vendors with products doing 2110, sending it or receiving it or multi-viewing it or test pattern generating it, or scopes that receive 2110, so forth. So that was a tremendous industry event. There was earlier, meaning let's see, that was in April. So I think in February or January we had a sort of a more detailed engineering interop that was really sort of the earliest vendors getting their initial true interops going. And then we had one also before IBC. So there have been now at least 4, I think, maybe more, sort of public industry interop events. So all the usual suspects, all the large vendors, most of the medium-sized vendors as well, have now been to these interops, have tested equipment against each other. So there's a very high degree of maturity of the, both the document and some of the implementations, where we've really proven to each other that we've all read it the same way. The same is true of SMPTE 2059, by the way. That group as well has done a large number of interop events where, everybody brings their timing generator. Many people bring their PTP slaves as well. And we test that, we all generate the sync edge at the same time. We all generate the same time code. We all participate in the grandmaster failovers and things the same way. So both of these have had a large amount of interop activity, more than I remember ever doing in any previous standard.
Good. Let's see. Ronald wants to know how much of the 2110 stream is dedicated to ancillary data, and is there a maximum number of network hops supported?
There's no maximum number of network hops. When you in IP in general, when you send a packet, there's a time to live field, and so if you go through enough hops, the network will stop forwarding your packet. So there is a fundamental limit, because that time to live field, I think, is only an 8-bit field. That said, as the name of the standard talks about, managed IP networks, it's not typical to have a huge number of hops. And if you do, you're likely to get into issues of accumulated jitter and so forth. So you'd have to design a network pretty carefully if it was going to have a large number of hops. I'm sorry, I forgot the other half of the question. There was hops and there was something else.
How much of the 2110 stream is dedicated to ancillary data?
So there's no dedicated bandwidth for ancillary data. Instead, the ancillary data is its own stream, so you can, in principle, send as much or as little as you have. There's no spec that says how much ancillary data a receiver has to be able to eat, and that maybe is an interesting topic that I'll bring up in the drafting group, because it is, it is sort of an interesting topic. But there's no real limit about the standard itself right now that says how much ancillary data there has to be. It's really just however much you want to send, you could send it.
Mm-hmm. Okay. We're making progress on the questions. We have 3 left. Lauren asks, any issues running over IPv6?
Well, it's really up to device by device the extent to which people support IPv6. So the standard specifies, that devices do IPv6 or do IPv4. We actually took the same approach that AES 67 took in that regard, which is that to do it, you have to do IPv4, and you should do IPv6, but I've never actually seen a lot of evidence that anyone's really tried this on IPv6. There's nothing about the 2110 standard itself that's actually different in IPv4 or IPv6, and we designed the payload to leave sort of enough space that you can still use standard Ethernet packets, Ethernet size packets, when you have an IPv6 header, because of course the header's bigger. So we did reduce the packet size to make room for the IPv6 header, but that's really the only accommodation we had to make. Everything we did in 2110 is kind of the same, whether it's IPv4 or IPv6. But for example, like the SDP examples in the standard and things like that, all those examples are done in IPv4.
Henning asks, how do unicast streams fit into 2110?
So most devices support unicast, so you can unicast, but of course when you unicast, the signal only goes one place. And if you're okay with that, that's great. The signal format's the same whether it's unicast or multicast. But the typical use case, as we understand it today, usually is that senders send on multicast groups and then receivers tune into that group. But there's nothing really that prevents unicast from being used in situations where that's what you need to do.
Okay, Henning asks a question. I'm not sure I understand it, but maybe you do. He asks, narrow, wide in audio?
So in the 2110 video standard, when we talk about how is the traffic shaped, there's a traffic shaping part of the standard. We actually define narrow and wide receivers and senders having to do with the amount of packet delay variation on each. For audio, we defer to AES 67, which has a, I'll say, less precise specification about traffic shaping. We didn't try to re-engineer their work on that. The AES is actually themselves working on revision of AES 67, so if they've got more experience in the field than we do with use of AES 67, so it's kind of, they're looking at all the aspects of AES 67 in their own revision work. But we don't specify anything additional about traffic shaping or narrow and wide and so forth for AES 67. We've sort of deferred that aspect of the audio to the AES.
Okay. And our final question for today, Yovo, I think, is going to ask you to look into your crystal ball. But actually, another one just popped in afterwards, so I'll ask this one first. Yovo says, the industry, he feels the industry is kind of slow transitioning to 2022-6. He says that 2110 brings all the flexibility 2122-6 lacks, but complexity and likely lengthy adoption times. What do you anticipate with regard to 2022-6 versus 2110 adoption for the next few years?
I think both will be used in different situations. 2110 gives you the flexibility to breakaway route all the audio, to breakaway route the ancillary, do all these flexible things, but it brings, of course, with that the complexity that you have to actually set all that stuff up. There's many facilities where the last thing you want to do is to accidentally break away the audio, because say in a playout center or something, keeping that package together is vital. So 2022.6 has a maybe a better complexity versus effort trade-off. That said, the other situation where 2022.6 is quite useful is in long haul, where if I'm sending things from one facility to another and they're on different timing domains, then the 2022.6 has the advantage of being call it a self-timed signal, that when you get an SDI effectively, which 2022.6 is SDI over IP, the process of taking that with the video and the audio and synchronizing it and time-based correcting it into the new facility or the new facility's timing domain is kind of handy. So there are examples of, particularly long-haul applications or crossing timing boundaries where 2022.6 still will have some interesting utility. That, and there's a little bit of just industrial momentum that people started implementing 2022.6, 2-3 years ago. There's a fair bit of product in the field. 2110 is still a little bit newer, but I believe that most people who are involved in the industry will have 2110 product very quickly. Within AIMS, the Alliance for IP Media Standards, we actually did a survey of our members, and the vast bulk of them said, yeah, we're going to have 2110 product within the calendar year. So there will be a lot of 2110 product. IBC will be, full of 2110 stuff, as NAB kind of was, and adoption of both will go on, I hope, for years and years.
Okay. And our final question is from Derek. Is there a specific 2110 essence synchronization field, or does it strictly rely upon underlying time code or PTC methods or out-of-band PTP timing?
So, as I said at the outset, PTP is used for establishing a common time base among all the endpoints, and then the RTP timestamps are derived from PTP, and so you compare the RTP timestamps to among the essence elements to resynchronize them.
Great. And that concludes our webcast. I would like to thank you, John Myatt. Did I get it right?
That's just fine, thanks.
Yes, thank you for putting in the time to create the PowerPoint and to explain this, I think, very important standard that a lot of people have interest in. I would also like to thank our guests for taking time out to attend and participate and ask questions. So with that, take care, safe travels, and we'll see you next time on a SMPTE webcast. Bye now.